Good afternoon, all the participants. Today, this is the third lecture in the series of nuclear reactions and production of radioisotopes. In the last two lectures, I discussed the basic principles of nuclear reactions and also different types of nuclear reactions in terms of their mechanism, like elastic scattering, inelastic scattering, direct reactions, and the compound nuclear reaction. Today, we will discuss the reactions induced by different types of projectiles so that we can go into minute details of how different projectiles interact with the different target nuclei. So in this lecture, we will discuss the reactions induced by neutrons, the charged particles. The charged particles will have light charged particle induced reactions and the heavy ion induced reactions. And lastly, the photon induced reactions. I will not go into too much details of the mechanistic aspects of these reactions, but just gives you a glance through certain aspects of these which are useful in understanding the mechanism as well as using them in producing radioisotopes. So the neutron induced reactions, it will be nice to know what are the different sources of neutrons that we can use in studying these neutron induced reactions. So as all of you know, the best source of neutrons is the nuclear reactor itself, which is like a sea of neutrons. The large volume of the nuclear reactor core gives you opportunity to irradiate several targets at a time, and the radioisotope production, in fact, is, you can say, the large bulk of the radioisotopes produced using nuclear reactors. But in universities, the small neutron sources can be very handy to do research in this field. So I have listed some of the neutron sources which can be housed in a room, a small room, like californium-252, which undergoes spontaneous fission, and the half-life of californium-252 is 2.54 years. This isotope emits alpha as well as undergoes fission. The alpha to fission ratio is 32, and 1 nanogram of californium-252 gives about 600 fissions or about 2000 neutrons. So if you take a milligram of californium-252, you will have 10 to the power 9 neutrons per second. And so you can see, you can have a mini reactor if you have 1 milligram of californium-252. Some of the universities in the early 70s had, in fact, these californium sources wherever the research on neutron induced reactions were going on. Another important neutron source is americium beryllium source. In this source, the alpha particles from americium interact with beryllium-9 and give rise to neutrons. And the half-life of americium-241 is 433 years. So you can see, once you have a americium beryllium source, you can go on using it for years together. In fact, this becomes a problem if the source is not in use, then you have to still maintain it. So there are short-lived neutron sources like polonium-210 beryllium neutron source. Again, the alpha from polonium-210 will bombard beryllium-9 and give rise to neutrons. And the half-life of polonium-210 is 138 days. So after a few years, this source can be discarded. And this type of sources are used in starting up of reactors or different applications where you don't need the source after some time. In the same category, we have this antimony beryllium source. 124 antimony is a 60 days half-life, and it emits strong gamma rays of almost 2.5 MeV. And these gamma rays then bombard with beryllium-9 give rise to neutrons and to alpha particles. So this is also another very useful radioisotope. Using photoneutron reactions, you can use this for production of neutrons. Of course, today there are spallation neutron sources where you have almost GeV proton beam bombarding a high Z target like tantalum, and by spallation, large number of neutrons are produced, almost 30 to 35 neutrons per proton interacting with the target. And these neutron sources now are replacing the reactors, because whatever research you can do with other than the radioisotope production, you are doing neutron scattering, small angle neutron scattering, you can do with this source. So in fact, in Oxford, in UK, they have shut down the reactor and now are using this spallation neutron source for neutron scattering type of experiments. So this is a new source where a lot of innovations have taken place in producing neutrons and you can thermalize the neutrons and use thermal neutrons, or you can use high energy neutrons. So a lot of innovations have taken place in terms of the neutron sources. Now, neutrons are actually classified based on their energy and also the way they interact with different target nuclei. So the most common are the thermal neutrons. That means when the neutrons are thermalized in the environment, ambient conditions, so the average energy of neutrons at room temperature, let us say 298 Kelvin, will be 0.025 electron volt. That is the average energy. So you have a distribution of neutrons around this energy, average energy. So like reactors, reactors are a pool of thermal neutrons, but there will be fast neutrons also in the reactors. So depending upon the type of moderator or the reflector, you will have a pool of neutrons. Then above this 0.5 electron volt, you have thermal neutrons, epithermal neutrons. This is the energy range where you may see resonances in the neutron-induced reactions, and so there are large cross sections in this region. So they are, in fact, for the specific target nuclei, they are very, very useful. So epithermal neutrons are also used some particular application. For example, you can have epithermal neutron activation analysis. So you want to activate a particular target which has resonances in this energy range, then you can study them specifically, selectively. And then fast neutrons of energy more than 1 keV. So you will be almost now populating the target nuclei or the compound nucleus in the continuum domain, so that you don't see much of resonances. You will see the behavior of a compound nucleus which is populated in the continuum. Okay, let us discuss a little bit more about the neutron-induced reactions. So the most common types of nuclear reactions are neutron capture reactions, wherein the neutron is captured by the target nucleus, let us say AX, and then you have the compound nucleus A plus 1X. So I have tried to explain this using this cartoon where neutron plus X, element X with mass number A neutron combines with this target nucleus and forms the next isotope of X, A. So it is A plus 1X. And the energy brought in by this neutron is equivalent to the binding energy. The Q value for this reaction is mass of neutron plus mass of target nucleus minus mass of the compound nucleus. And this is nothing but the binding energy of neutron in this nucleus. So this is always positive. And so the compound nucleus is populated with energy equivalent to binding energy. So typical binding energy will be about 7-8 MeV. So the compound nucleus is excited to the energy of about 7-8 MeV. And this excited nucleus, the gamma ray, the energy brought in by the neutron is shared among all the nucleons of the compound nucleus. And so invariably, it will be emitting the gamma rays because the possibility of particle emission are very less in normal cases. There are exceptions which I will discuss shortly. So this excited compound nucleus then emits gamma rays within a very short time scale, minus 12, 10 to the power minus 12 seconds or less, and they are called the prompt gamma rays. So the neutron-induced reactions are always exergic, like I have given this example. And after the neutron is captured by the nucleus, the compound nucleus invariably emits gamma ray. That's why it is called the radiative capture. With thermal neutrons, particularly, you have this kind of reactions. And this the products of this radiative capture reaction are most often beta minus active, because you are increasing the neutron to proton ratio. So when the N by Z is more than the stable isotope, you will find the predominant mode of decay is beta minus, like 197 gold and gamma 198, which will be emitting beta minus to 198 mercury. Of course, there are different types of reactions taking place with neutrons, particularly with the light nuclei. So when you have the lighter elements as target nuclei, like aluminum, silver, sulfur, chlorine, and so on. So this low Z nuclei, because the binding energy of charged particles like proton and alpha, as well as the Coulombic repulsion, Coulombic barrier for emission of these particles is much low. So whatever the energy that neutrons bring in, that is sufficient to emit the charged particles. So the kind of reactions like NP and alpha are very common with the lighter nuclei, and in fact they are used to produce useful isotopes. For example, sulfur 32 NP reaction, phosphorus 32, chlorine 35 N alpha reaction, phosphorus 32, aluminum 27 N alpha reaction, sodium 24. So you can see here that in the case of light nuclei, because the Coulombic barriers for emission of proton and alpha particles are very, very small, the excited compound nuclei can emit alpha particles also. Whereas in the case they will also have N gamma type of reactions, but these charged particle reactions are quite dominant in the light mass nuclei. Then, whereas the N gamma reaction is most common in entire range of mass number, and particularly in the heavier mass, this is the only mode of decay. For example, gold, 197 gold N gamma. This is the only. So you take rare earths or even the transition elements, you will find for mass number more than 50 or so, the N gamma is the most common mode of reaction for the target nuclei. But less than 50, where the alpha particle or proton emission barriers are very low, you will have NP and alpha types of reactions. Now, in the case of actinides, there you will have N gamma reaction anyway, but in addition to the N gamma, you will also have neutron-induced fission reactions, which are common, like 235 NF neutron-induced fission, wherein two fragments are produced, F1 and F2, and you have 2 or 3 neutrons. 239 plutonium also you will see neutron captured followed by fission, and then emission of 2 fragments and neutrons. So in fact, these two isotopes and also 233 uranium can undergo fission with thermal neutrons, whereas other isotopes like uranium like 238 or even 240 plutonium or thorium 232, they cannot undergo fission with thermal neutrons. But if you have higher energy neutrons of 1 MeV or so, then they will also undergo fission with the neutrons. So neutron-induced fission of actinides is a common mode of reaction. Of course, they also have N gamma types of reactions. Now, the cross section for the neutron-induced reactions I have tried to explain a little bit briefly. So, as I discussed in the last lecture, the sigma n for neutron-induced reaction, pi r plus lambda cross square, where r is the radius of the target nucleus. You can neglect the target neutron radius, and the reduced wavelength of the neutron. For low energy neutrons, the wavelength of neutron is very high compared to the radius of the target nucleus, and therefore we can neglect this capital R compared to lambda cross. So cross section for neutron induced reaction becomes pi lambda cross square T0, where T0 is the transmission coefficient for the L equal to 0 neutrons or S wave neutrons. Now, for low energy neutrons, as I mentioned, L equal to 0. So the transmission coefficient can be calculated using this formalism. I have just given a brief introduction to that. That is when the neutron is coming from outside and it is amalgamated with the target nucleus. Outside the nucleus, the momentum of the neutron is very small, whereas inside the nucleus, it has got a very high momentum. You see, the kinetic energy of these protons and neutrons inside the nucleus is quite high, because this is nothing but the potential plus the binding energy. So the kinetic energy is very high, maybe 20-30 MeV, whereas the outside it is very small. So you'll find that neutron has very low momentum outside and very high momentum inside the nucleus. So you can set up in the formalism of optical model, the wavelength of the neutron outside the nucleus is a plane wave. It is a factor a e raised to ikx, plane wave coming, and the incident inside the nucleus you can write in some sort of spherical wave e raised to ikr, capital K. And so you can set up the equation, find out the transmission coefficient for this reaction, and is nothing but transmitted flux upon the incident flux. Actually, here one term also will come, reflected. This is the transmitted plus reflected a e raised to minus k ikx. And so you can calculate this flux from the square, the intensity of these two waves, taking the square of that will get the flux. So by solving these equations, the wave functions and their derivatives, continuity of the wave functions at the boundary, we can find out the transmitted flux and incident flux, and thereby the transmission coefficient. And for the neutrons, that comes to be 4 kk upon k plus k square, where small k is the momentum outside, capital K is the momentum inside the nucleus. Now, since the capital K is very large compared to small k, you can neglect this small k here, and so this one big K will get cancelled out, and so transmission coefficient becomes small k upon capital K. So you can substitute in this equation sigma n pi lambda per square, small k capital K, and so you can approximate this to 1 by V, where lambda is 1 by V, so lambda square 1 by V square, and the K momentum outside is proportional to V, so 1 by V square into V 1 by V. So this explains the 1 by V dependence of the cross section for neutron-induced reaction in the low energy away from the resonances. For the resonance reactions of neutrons, Reed and Wigner have given a formula for cross section, calculating cross section for resonance in nuclear internal reactions, that is given by this formalism. So if you have a reaction A, capital A comma B, capital B, A is the projectile, B is the ejectile. Like here, you can put A is neutron and small b is the gamma ray. Then sigma AB is pi lambda per square. This is the multiplicity factor. I are the spins of the projectile, the spin of the target, and the spin of the compound nucleus. And this is the factor into gamma A, let us say gamma A. This is a width for the gamma emission. This is a width. This is width for the neutron emission, width for the gamma emission. So gamma A, gamma B, width for the emission of these two radiations upon epsilon minus epsilon 0. So epsilon is the energy at which you are calculating the cross section, and epsilon 0 is the energy at which resonance is occurring. So epsilon minus epsilon 0 square plus gamma by 2. Gamma is the total width. So gamma means gamma A plus gamma B. If these are the only two modes of decay, then gamma is gamma A plus gamma B. So the gamma by 2 square. So this is very, very successfully, this formula calculates the cross section for the resonance cross sections in resonance and also little away from the resonances. So this is the formalism people use to calculate the cross section for neutron-induced reaction in the resonance region. Now, neutron-induced reactions are widely used in many applications. Of course, production of isotopes is one of them, which I will discuss more in detail in the coming lectures. But in addition to that, neutron activation analysis is widely used in different subjects, wherein you determine the concentration of the elements in a sample. So how do you determine the concentrations? the activation equation. That means we irradiate a target in the reactor, then you get the activity by N-gamma reaction. And if you measure the activity of the products which are radioactive, then that activity at the end of irradiation can be given in terms of n sigma phi 1 minus e raised to minus lambda Ti, where n is the number of target atoms in the sample. Sigma is the flux, sigma is the cross section for that reaction, and gamma, let us say, phi is the flux of neutrons, and this is the saturation factor 1 minus e raised to minus lambda Ti. Lambda is the decay constant of the radioisotope. Ti is the time of irradiation. Now the number of target atoms, usually you will take some W grams of the target element. If the target is not monoisotopic, then it will have different isotopes. And so the abundance of that target, the particular isotope which is being activated, will be coming into picture. And C is the concentration. So W is the amount of sample, let us say gram. In that, this many micrograms is the C concentration, let us say ppm, microgram per gram. So in W gram, that many micrograms, and out of that gram of that target element, this is the number of, this is the abundance of the isotope of interest. And so this many gram, this many atoms in a gram. So you can calculate number of target atoms. So W is the weight of the sample, C is the concentration of the element in the sample, A is the abundance of the isotope activated in the element. So, for example, this technique can be used to find out the concentration of elements in environmental, archaeological, forensic, biological, and many other types of samples. Like you want to determine arsenic in human hair. If the person is poisoned with arsenic, then from the human hair concentration with arsenic has a tendency to go in human hair. You can determine arsenic concentration by neutron activation analysis. Uranium concentration in the groundwater you can find out by activation analysis. Determination of trace metals in air, water, soil, marine, etc. type of samples you can determine by neutron activation analysis. One of the examples of neutron-induced reaction. Okay, now I come to the charged particle-induced reactions. The charged particle sources I have just listed here. Cyclotron is one of the most commonly used source of charged particles. We can also have very high current of charged particles, almost milliamperes. 1 milliampere will have 10 power 15 particles per second. And so the basic equation for a cyclotron is mv square by r is equal to bqv. mv square by r is the centripetal force on the charged particle moving under the force of a magnet. And so this is a magnetic force. So the magnetic field, the charge, and the velocity. And so from here you can find out the velocity and hence the energy of the ion. So it depends upon the magnetic field, the charge, the radius of the D's, where the charge particle rotating, and the mass of the charge particle. So you can calculate the mass energy of the charge particle in a cyclotron using this formula. In the Van de Graaff, as I mentioned in the previous lecture, it is a one-step acceleration where you have a terminal of V volts. So the charge Q will acquire the energy QV. This is the energy. You cannot go to very high energies in Van de Graaff. And so Van de Graaffs are not that much common these days. Instead, you have a linear accelerator where you have, like, instead of cyclic acceleration, in a linear acceleration, you have the large number of linear tubes, and there is a successive acceleration in different tubes. So there are n stages of acceleration. In every stage, you accelerate by q into v, and so you have n into q into v, and the n can be very, very large. So you have again the alternative current and the frequency, the potential changes alternatively between the successive accelerating tubes, and you can accelerate to very, very high energy. And then you have the peloton accelerators where you start with the negative ion up to terminal potential V. So the negative ion acquires V volts, V electron volt, and then the strip of the ion electrons So the Q plus charge state is repelled by the terminal potential. So Q plus 1 into volt is the energy. Suppose you have 14 million volt, then Q plus 1, like carbon 6 plus 1. Suppose you strip all the electrons from carbon, then you will have 6 plus 1, 7 into 12, 14, 84 MeV carbon you can have. So that is the kind of energy you can get in electron. Okay. So the charge particle induced reaction, I have tried to segregate into light charge particle induced reaction and heavy ion induced reaction. In the light charge particle induced reaction, protons, neutrons, and alpha particles are commonly used projectiles. So with the it is like with any charge particle fusing with the target nucleus, we have, like say, oxygen 18 PN reaction F18. This is a reaction used to produce F18, which is a PET isotope. You can have cadmium 111 PN reaction, indium 111. Indium 111 also used in nuclear medicine for diagnostic applications. Zinc 68 P2N, gallium 67, helium 201 P3N, lead 201, and this lead 201 decays to thallium 201, which is used in the stress test analysis in SPECT imaging. Iodine 127 P3N, xenon 125, iodine 127 P5 and xenon 123. They are also used in diagnosis or therapeutic applications in nuclear medicine. So, in case of proton and light charge, the neutron-induced reactions, we have the charge particle amalgamating the target nucleus, followed by emission of neutrons, protons, and alpha particles. Neutron-induced reaction, DP reaction, you can have these transfer reactions of this type, DP reaction. Deuterium is stripped of the proton, and the neutron is fusing with the target, or neutron can pick up a neutron, or it can be stripped of a neutron, like that. So these are the type of reactions which can occur. Neutron, alpha particle induced reactions, you have alpha 2n, alpha 2n, alpha 4n, different types of reactions. So once a alpha particle is forming a compound nucleus with the target nucleus, the compound nucleus has the excitation mode of emission of neutrons, even protons, or even if you have very heavy nuclei like uranium, it can undergo fission also. So light charge particles will have this type of reactions taking place. Now, how do cross sections vary for these charge particle induced reactions? The variation of the cross section of individual products with the energy of projectile is called as the excitation function. For example, if you have a alpha particle bombarding a niobium 93 target, forming a compound nucleus technetium 97, then this excited compound nucleus can de-excite by emission of neutrons. So you can have an emission of 1 neutron, 2 neutrons, 3 neutrons, depending upon the excitation energy, giving rise to different evaporation residues. So the cross section for the nuclear reaction, alpha particle induced reaction, is sigma r. That is the reaction cross section. Sigma r is going to vary like pi r square 1 minus Ec by ECM that I derived in the previous lecture. Now this reaction cross section is composed of cross sections of individual products. So in the initial, when the energy of projectile is low, compound nucleus has low excitation energy, so you have only 1 neutron emitted, and at higher energy of alpha particle, then excitation energy becomes more, so that 2 neutron emission becomes possible, and so 1 neutron probability starts decreasing. After it reaches maximum, the energy of alpha becomes so high that 3rd neutron may start emitting, and therefore alpha 3n starts increasing. So the rise and fall of this excitation functions for individual evaporation residues is a typical feature of compound nucleus reactions. And if you want to find out at any particular energy what is the total reaction cross section, you can sum these cross sections and arrive at this one. But mind you, these are all, suppose you are measuring by offline gamma spectrometry, there could be some evaporation residues which are stable. So this method may not measure those products. So if you want to measure all types of products, probably you have to go for online gamma spectrometry, or you measure the evaporation residues like neutrons and so on. If all of them are evaporation residues are radioactive, then you can use this method to determine the total reaction cross section. But this excitation function measurements are very useful when you want to fix the energy of projectile to produce a particular radioisotope useful in your application. So suppose you want to produce technetium-95 for a particular application in some field, and you want to know what is the energy at which you should bombard the target nucleus to produce maximum activity of 95 technetium. So what you do, normally, the research worker, the scientists, the nuclear physics or nuclear chemistry people have already studied this excitation function. So based on this literature or your own experiment, you can find out that if you bombard with this energy of alpha particle, you will produce the maximum activity of technetium-95. In fact, if you use a thick target, then this entire cross section you can make use of. So when the alpha particle is losing energy in the target material, this cross section also will be utilized. So by thick target, we can produce high activity of this evaporation residue. That is the application of excitation functions. How do you measure these excitation functions? As a function of energy. I have given an example for offline gamma spectrometry. So wherein you take a projectile and bombard the target. So suppose you want to determine the excitation function means as a function of energy. So what you do, you have thin target files. These red ones are the targets, and the blue ones are the catcher files. Catcher means once the projectile bombards the target, some of the products may come out of this target, and then you have to stop them in a catcher file. So this is a pair of target catcher wherein you can trap the evaporation residues of a reaction at one energy. Then you, by the time this alpha particle is coming here, energy of the alpha particle has decreased. So this is another energy alpha particle bombarding this target, and you capture the products in this. Some of them will be captured here also. This pair will give you cross section at another energy. Like that, this pair. So you have 1, 2, 3, 4, 5. So 5 energy of alpha particle or proton, whatever is the projectile. In one go, you can measure the cross section for 5 energies decreasing from here. So you just count them, separate them, and count them in a gamma detector, and from the activity you can find the cross section. So this is the activation equation for radioactive evaporation residues. In the activation analysis, you determine the N. You want to determine the cross section. You know the target atoms per centimeter square. From the thickness, you can find out the number of atoms per centimeter square. I is the intensity of the beam. You can use measured by Faraday cup. Put here Faraday cup and divide by time, becomes total charge upon time is current. This is a saturation factor for the growth of the radioactive isotope. And if after end of irradiation there is some time t has elapsed, then the decay of the radioisotope after end of irradiation e raised to minus lambda t. And then when you measure the gamma ray has got a certain abundance. That means this isotope may be beta minus emitter. Every beta may not give this gamma. So out of 100 beta, how many gammas are emitted? This is the gamma ray abundance. And when you detect the gamma ray in a detector, then you will have the detection efficiency. So all these factors have to be known to determine the cross section for that reaction. So by measuring the sigma at a particular energy, you get sigma versus E. That is what is the excitation function. The different products, you can isolate in this target catcher pair by gamma spectrometry. You use high purity germanium detector wherein you can resolve all the gamma rays of the residues. So multiple products you can determine in one experiment. Okay. Measurement of ejectile spectra and angular distribution. Suppose you are doing online experiment wherein you want to determine the emitted particles like protons, alpha, neutrons, and so on, and do detect angular distribution. So here I have shown a photograph of a scattering chamber. Normally, in the scattering chamber, you will have a 1 meter dia, big scattering chamber, because you want to vary the angle very, very minutely, maybe millisteradians. So you have a target ladder here. Target ladder, you mount the multiple targets, and then the detectors are placed in. There are 2 detectors here. You can see here. So you can put multiple detectors at a particular angle. And so basically you will have, if you are determining the charged particles, you have to resolve the charged particles like proton, alpha, So you require a delta EE telescopes based on surface barrier detectors. And so you have this chamber at very high vacuum, 10⁻⁶ star. And after you irradiate, then online you are determining the counts in this charge per incidence, which are the control dome. You will have the control system. With the analyzer, you can find out the spectrum. So the counts that you measure in a particular detector has a particular angle you have the detector. So number of atoms per centimeter square. The differential cross section. Now the cross section depends upon the angle. So d sigma by d omega. Omega is the solid angle. So per unit solid angle, you determine the cross section and the total charge. Total charge is nothing but the current into the time. So you determine the cross section by this experiment, and you can integrate over the angle to find out the total cross section for that reaction. Total number of incident particle you determine in the Faraday cup, and then that you can, if you want to determine the current, you can. In fact, in this reaction, you don't need the current. Total charge collected is if required. And for identifying the particle, delta E telescope is used, where you have a thin delta E detector, surface barrier detector of the order of 15 to 20 to 25 micron thick, and the thick one will stop the charged particle totally. So this pair can be used to identify different different fragments. So you can resolve the different particles, proton, alpha, and so on. So this is a typical online experiment to find out the cross section for nuclear reactions. Okay, how to choose the projectile and its energy. So I thought this exercise can be used. Like one of the methods was to find out the excitation function, but you can have one rough way of determining the energy of projectile to produce a particular isotope. For example, let us say we want to produce thallium-201, which is used in oncology for the SPECT imaging or stress test analysis. So this thallium-201 is produced in this reaction. Thallium-203 P3N reaction, lead-201, and this lead-201 undergoes beta plus or electron capture decay to thallium-201. So you can separate lead from thallium, the target material, and then lead will decay to thallium-201 by electron capture. It is not beta minus, I think it is electron capture. So the target is thallium-201, projectile is proton. And now what we want to know, what we want to find out, what is the energy of proton to optimize the production of thallium-201. You are doing a cyclotron experiment. What should be the energy of projectile? So let us calculate the Coulomb barrier. The Coulomb barrier is 1.44 or 4382 Z1 Z2 by R0, A1 1/3, A2 1/3. So if you put these numbers, you get 13.2 MeV. And this is the reaction. So 3 neutrons are emitted in this reaction. So what will be the excitation energy of lead-204 compound nucleus? Is nothing but ECM plus Q. So Q value for this reaction is mass of proton plus mass of 203 thallium minus mass of 204 lead. That is equal to 6.7 MeV, 743 MeV. This is the Q value. Now, what is the energy of proton? So ECM plus Q has to be around 30 MeV. Because to emit one neutron, roughly you require 10 MeV, because binding energy is of the order of 7-8 MeV, plus a neutron will come out with 1.5 MeV energy. So typically, 10 MeV energy is used in removing one neutron from the compound nucleus. So for 3 neutron emission, 3 into 30, about 30 MeV energy is required. So the compound nucleus should have 30 MeV excitation energy. 6.7 is the Q value. So ECM will be 30 minus 7.743. It should be 6.743. So 23.257 MeV. And so if ECM is 23, what should be the laboratory energy? You know the ECM to laboratory energy. This into 204 by M1 plus M2 by M2. So about 23.37 MeV. So if you have about 24 MeV proton bombard the target of thallium, you will have optimum yield of thallium-201. So this is the exercise to demonstrate how to choose the energy of projectile to produce a particular radioisotope. Okay. The heavy ion reactions, now I have put them in a different class because unlike the light charge particle induced reaction, where mostly you have fusion reaction as a common mode of, and there are of course direct reactions with neutron, the loosely bound particles. I try to separate it because it opens up a lot of avenues for the studies of nuclear properties. So I just give you a background that if you have a heavy charge particle like carbon, oxygen, neon, any heavier, so let us say lithium onwards, so we will say they are heavy ions. And so when this when this heavy ion is approaching the target nucleus, then you have to also consider the different forces that are operating. So if you have the pure Coulombic interaction, that is Z1, Z2 E square by R, so this is the VC Coulombic barrier, will repulsive potential for the repulsion between the charged particle and the nucleus, target nucleus. Whereas at a shorter distance compared to the Coulombic force, the nuclear attractive force will start operating. So this is the attractive nuclear potential. And the sum total of these two, if you sum them, you get this kind of a potential for the projectile target combination. And what you see here, this is called the one-dimensional potential energy barrier. This shows a barrier here that is called the fusion barrier. So if the projectile has to fuse with the target, then the projectile should be trapped in this pocket. The pocket is formed. Pocket is like a minimum in this one-dimensional barrier. So you have to have energy of projectile should be more than this fusion barrier. So this fusion is the common nuclear reaction between the heavy projectile and target nucleus. But then what happens? Whatever this I have drawn for a L equal to 0, that means the angular momentum is 0. But the moment you bring in heavy ions as projectiles, I didn't discuss this in case of light ions because light ions don't bring that much high angular momentum. But the heavier ions will bring large amount of angular momentum. And the angular momentum is also a repulsive, brings a repulsive force. So that L plus 1 h square by 2I, that will add to this repulsive potential, Coulomb potential. So this ELR will become repulsive potential. And so for the different L values, higher L values, this potential will start becoming more and more shallow. So when this becomes more and more shallow, you will find that slowly this potential will vanish. And therefore, when you don't see a pocket in this potential barrier, you will find the complete fusion becomes difficult to take. So you will find other mechanisms opening up when you have projectiles of heavier mass. So I tried to show them in this diagram the angular momentum dependent cross section as a function of L. So for the lower angular momentum, as long as this pocket remains, you have the complete fusion. The projectile and target nuclei fuse together completely. So you will find that the compound nucleus is formed, and the de-excitation of compound nucleus depends upon the whatever channels are available for it to decay. But for higher angular momentum projectiles, you have incomplete fusion. And if you have a very heavy projectile, they have then deep inelastic collisions. These are the type of non-compound nucleus reactions where you will find that compound nucleus is not formed. And in fact, this itself is subject of study for the nuclear physics community. And for the last window, we call the quasi-elastic transfer reactions, where they are like grazing collisions. So the projectile and target just graze through each other, wherein a few nucleons are transferred between them. So they are actually mostly like a Coulombic scattering, but there is an exchange of particles between the two. So the different reactions that occur when a heavy ion is bombarding the target nucleus: incomplete fusion, complete fusion, incomplete fusion, deep inelastic collisions. In fact, once you have the heavy ions bombarding heavy target nuclei, then fission becomes a dominant mode of decay. and with the higher angular momentum, the fission barrier further comes down. So it's called a rotating liquid drop model. So liquid drop model is normal fission model, but if you bring in angular momentum, the fissioning nucleus is rotating also, and so that will reduce the fission barrier. So this is called the RLDM. And as a consequence of this RLDM, there are other mechanisms called fast fission. That means the barrier of the nucleus, fission barrier becomes zero. So for a particular angular momentum, fission barrier becomes zero, higher L values undergo fast fission. Then there are quasi fission and there are quasi transfer reactions. So these are all, we don't have to go into details of these different reactions, but this itself is a subject of study. Many of the participants probably, as I can see, they are busy, they are actually involved in this kind of studies. I could see from the questions that they have raised in the last lecture, some of them are doing study of this type. Just to give an example of this heavy ion reactions, this is something which I have done some experiments in the 1990s. That is the incomplete fusion reactions. This incomplete fusion reaction, why it is called incomplete? Because one is that the projectile does not fuse with target completely. Incomplete fusion also, it is characterized by incomplete momentum transfer. And so I thought I will show you how an elegant experiment can be planned using this reaction I have tried to show. So what I am showing here, you have a reaction bombarding carbon bombarding niobium 93, forming a compound nucleus silver 105, and it is evaporating neutrons. So this is the evaporation. Actually, this should be silver 101, not palladium. This complete fusion reaction. And so this complete fusion reaction gives you full momentum transfer. So this is what I have measured here is the range of this evaporation residue. Like palladium 101, you also have silver 101. That will decay to palladium 101. And so this is giving you full momentum transfer. So I tried to explain here using a experiment called recoil range distribution, wherein you have a target, thin target, and the evaporation residues are coming out from this target and stopped in different catcher files, which are very thin catcher files. So when you have a full momentum transfer, the evaporation residue has a very high energy and it is stopped in this catcher file. But when there is a incomplete momentum transfer, like here, in this case, the complete fusion, this compound nucleus emits alpha, evaporates alpha, and this is formed 101 rhodium, which is emitting a neutrons to give 199 rhodium, and that is shown here, 99 rhodium. But instead of this carbon fusing with the target nucleus, it breaks up into beryllium-8 and alpha, and beryllium-8 is going to fuse with the niobium, and alpha is coming out. And then this 101 rhodium is emitting neutrons. So this alpha that is formed here is not evaporated from compound nucleus, unlike in this case. So this is a reaction where momentum transfer is not complete. And so this particular product will stop in early foils. So because it has had low energy. So by the same product is formed by two reactions, you can resolve them into two depending upon what is the mechanism. So this you can see here in this 99 rhodium has got two components, the full momentum transfer event and the incomplete momentum transfer event. So by a very careful experiment of recoil range distribution, one can in fact deconvolute the linear momentum transfer involved in these two types of reaction. That is the kind of experiments one can do. Okay. Lastly, I'll come to the photon-induced reaction. In fact, last lecture, one of the participants was asking about photon-induced reactions. I already discussed about the photonuclear neutron sources, where you bombard the beryllium-9 target with gamma rays, and this deuteron and the beryllium-9, they are loosely bound particles, where the binding energy of neutron is very small. And so by bombarding the neutron with the target nuclei with the gamma ray of this order, you can see here 2.226 MeV gamma ray can break this neutron into the neutron and proton. And 1.666 MeV gamma ray can break this beryllium-9 neutron in beryllium-8. And beryllium-8 is unstable, so it splits into 2 alpha particles. In fact, if you go to high energy gamma ray, you can even split carbon-12 into 3 alpha particles. So a 20 MeV, at 20 MeV excitation, carbon-12 can be split into 3 alpha particles. In fact, that is what gave rise to what is called the alpha cluster models. This carbon-12, oxygen-16, neon-20, they are all clusters of alpha. There is a model of nucleus based on the. In fact, when you discuss the alpha decay from heavy nuclei, you also consider the pre-formation probability of alpha in the nucleus. So, essentially, there is an evidence that there could be alpha pre-formed in the nucleus, especially if it is an even nucleus. But the common mode of decay of a nucleus when it is excited to very high energy, one of the modes is by gamma emission. So a broad peak is seen in the gamma spectra. When the people are exciting the nuclei to very high energy, 20, 30 MeV or more than that, then people observed in the gamma ray yield a hump, a broad hump. And so this broad hump is so much broad, you can say almost 5 to 10 MeV of FWHM. This is not a normal statistical, the discrete gamma ray emitted from a compound nucleus, and particularly energies are around 15 MeV. So in the case of gold 197, this is found to be 15 MeV. So this was termed as explained in terms of the giant dipole resonance. That means there is it is like a dipole is de-exciting. So what do you consider? It is that the protons and neutrons are oscillating. The proton and neutrons are oscillating in the nucleus, and that oscillation gives rise to shaking away of this gamma ray as a dipole. So when a dipole is de-excited, the nucleus is like a dipole. So when this gamma ray is emitted, and in fact this has been found out in all the nuclei, and the energy of this maximum of this GDR maximum has been found to decrease as A minus 1/6. So essentially, it was found to decrease with 1/√R, where R is the radius of the nucleus, and so R to A minus R equal to R0 A raised to 1/3. So it has been found that in the case of oxygen, the GDR occurs at 25 MeV, whereas in the case of lead, GDR occurs at 15 MeV. So this the excitation of this gamma ray, the high nuclei, the emission of the broad gamma ray band has been observed, and now so you can use in the inverse reaction. You can use a high energy gamma ray to excite this mode in the nuclei. So how do you get these high energy neutrons? One is that you get from the Bremsstrahlung. You take high energy electrons and bombard them on your target. Then you have high energy gamma rays, or you can have a proton, a positron, and electron annihilation, and you can get the annihilation gamma ray. So you can have even the discrete gamma rays of very, very high energy to carry out this kind of reactions. So photonuclear reactions can be studied using Bremsstrahlung or annihilation gamma rays, and that is a subject in itself. I will not go into details. In fact, I am not an expert in the giant dipole resonance type of reactions. So those who are interested, last time there was a question asked about these reactions, they can go through this photonuclear reaction details in the literature. So that's all I had to say.